Going to pick up here with 7, which is chemical quantities and reactions. We talked a little bit about some of the stuff in chapter 7, so we will go through it and then we'll get into some of the calculation parts. All right, so chapter 7, really the first part here we're going to talk about again, just to make sure. I know we did it sort of a preview there in discussion the other week. Let's talk about equations and balancing equations. So again, when we do have a chemical reaction, the left-hand side of the arrow are reactants. So these are, again, our starting material in a chemical reaction. And on the right-hand side of the arrow, these guys are our products, which are obviously what is formed as a result, again, of this chemical reaction taking place. A chemical reaction is a chemical change, which means what we start with and what we end with are two fundamentally different things. We might also talk about some other things very commonly that you see in equations. Again, the states of everybody is very commonly found. So again, if you see an S next to something, that's in the solid state, and L is liquid, G is gas, and AQ is the aqueous state. And I think we also talked a little bit about the difference between these two, and there is a difference. Again, if something is in the liquid state, that is usually just a pure substance. And again, something like water by itself, nothing else with it, would get that liquid sort of symbol next to it. It is really when you take something like water and then take something else and maybe dissolve it in there, that you do get a solution which does get the aqueous symbol. So again, if you took some solid sodium chloride and you mixed it with some water, the sodium chloride would dissolve in the water, and that would make you a sodium chloride solution that would get the aqueous symbol. So really the aqueous symbol is for solutions, and solutions are homogeneous mixtures where everything looks the same throughout. So pretty much all your reagents that you use in lab, they're pretty much, if they are sort of the liquid state, they are aqueous solutions. They're usually made by dissolving something in something that's larger like water. Other things that we commonly, again, do see on equations, once again, the delta symbol sometimes used to indicate heat. Sometimes water is written up on top of the arrow to indicate something is being dissolved in water. And very often a catalyst is kind of written on top of the arrow there. And a catalyst is something that will speed up a chemical reaction. It is not a reactant. It's not a product. It doesn't actually get used up in the reaction, a catalyst. It is just there simply to really speed up that reaction. So for example, the experiment you were doing this week-ish, maybe, well, no, let's see, which was the gas one, you have some MnO2 in there, and that's really a catalyst. It's there to speed up that reaction. And if you don't use it, your reaction will take a long time. Now, we talked about the importance of balancing an equation, and whenever we have any type of equation, you want to make sure that it's balanced, and you should always check, even if you're given the equation, I would say definitely you should check if there's like no numbers in front of anything, for sure, to make sure that it's balanced. I would say probably in most cases we do see some numbers, unless they're trying to trick you. It should probably be a balanced equation, but you should always double check just to make sure. The idea here is, in a chemical reaction, as we might have talked about, the only thing that changes is we basically break apart all the bonds on the reactant side, and then we pretty much make new bonds on the product side. We never lose any elements along the way, so nothing is ever lost. We don't create new elements along the way either. It's just really a rearrangement of everybody that is present to start with. They break their bonds, they make new ones, and they make new products on their side. So because of that, we really have the conservation of the elements, which means in a reaction or equation, If you started with 4 oxygens on the left, you should end with 4 oxygens on the right. They may be in different sort of compounds on the product side, but you shouldn't lose any oxygens along the way. You shouldn't lose any elements along the way, because really the only thing that's involved in chemical reactions is electrons and bonds. And as we know, the only way to change a element into something new is to change what thing? What determines what element you have? The number of protons. So because protons and nothing in the nucleus is really involved in a chemical reaction, we never ever change elements along the way. The only time that happens is in a nuclear reaction, which that's pretty much all it does is play with the stuff in the nucleus. But in normal chemical reactions, since we're not going to talk about nuclear reactions here in this class, it's all about electrons and bonds. So we do have that conservation of elements. We talked about, I think, balancing equations there during discussion the other week. But again, the idea here is everybody kind of has sort of a different method. I personally like to make a table to sort of list what elements are there on the reactant and product side. So just kind of list all my elements. It also helps you sort of get a visualization maybe of where you should go to balance equations, where to start. Some people say you should start with the most complicated. I don't know. I think I start with whatever seems the easiest to sort of fix with a coefficient. But a couple important things about balancing, just to remind you, when we do balance equation, the only thing that we change are the numbers that come in front. So we only change the coefficients when we are balancing equations. So just those numbers that come in front. We never change any of the subscripts on the formulas. We don't put any numbers in between symbols or anything like that. Again, because you would change, obviously, what you're dealing with. Once you kind of fix something, it's very common in balancing that you kind of screw up something else. So you kind of fix one thing and mess up something else. And again, that's a very common sort of thing that will occur. But you just kind of keep back and forth. And then eventually everything should fall into place with the coefficients. When you are done balancing, there's 2 things that need to be done. Again, they need to be all whole numbers, the coefficients. And they also need to be, again, the simplest set of whole numbers. So as I might have put up there the other week, again, if you happen to balance equation with some numbers like this, although it may be balanced, you could go back through and divide everybody by 2 and still get whole numbers. And that would give you the properly balanced equation. A plus 2b goes to c in this case. And that's what you'd want to do. Now, as we saw in some examples, you definitely can, in some cases, use a fraction to balance the equation. But you do need to clear the fraction when it's all said and done. So when you maybe have to use a fraction, a lot of times that happens when perhaps you have a diatomic element by itself on this side and that element and a couple of things on the other side. So that's very common where maybe you have to use a fraction. When you're choosing the fraction, pretty much the top number is the number you need to balance out everything. And the bottom number should match the subscript that is sitting next to you. That way everything will match out sort of correctly. All right, so let's do a few more examples just to make sure. So let's balance this guy up here. So once again here, I personally like to make a little table. So we got reactant side, product side, and then again, just kind of list up our elements. So on the left-hand side here, we have 1 nitrogen. Right-hand side, we have 2. Left-hand side, we have 1 oxygen. Right-hand side, we have 1. And left-hand side, we have 2 hydrogens, and right-hand side, we also have 2. So in this particular case, clearly we can see that nitrogen should be a good place to start. So we will put a 2, again, the number in front there to balance it. That gives us 2 nitrogens. This 2 gets distributed to everybody behind it. So that gives me 2 oxygens, and we have 2 hydrogens at this point. As I mentioned before, this is very common. What happens, you kind of fix one thing, but screw up something else. But from our table, we can see really the next place we would want to go would be to the oxygen on the right-hand side. We have 2 on the left. So to fix the 2 there for the guy on the right, we're going to put a 2 in front of water. Once again, this is going to give me 2 for the nitrogen, and this 2 again gets distributed to both things behind it. That gives me 2 oxygens, and 2 times 2 is 4 hydrogen. Now we could fix this again by going to the left-hand side, and we're going to fix it by putting a 2 there as well. And that gives me 2 nitrogens, 2 oxygens, and once again, 2 times 2 there is 4. So this would represent, obviously, the balanced equation. Any questions on that one there? All right, let's try a few more here just to make sure we don't forget how to do it. All right, give this one a balancing job. And left-hand side for carbon, we got 3 to start with. Right-hand side, we got 1. Hydrogen on the left there, we have 8. On the right, we got 2. Left, we got 2 oxygens. And again, we do have 2 oxygens here, plus 1 more here, which does give us 3 oxygens to begin with there on the right-hand side. So again, for me, just looking at it, it seems like carbon seems like a very easy thing to fix. So we will put a 3 in front of it. And when we do, once again, this does get distributed to everybody behind. So that's going to be 3 carbons. We still have 2 hydrogens. Now, oxygen, we have 3 times 2, which is 6, plus 1 more over here makes 7 at this point. Next, I might want to look for the next easiest thing to fix, which would be the hydrogen. And we could easily do that by putting a 4 here in front of it on the right-hand side. That again gives us 3 carbons. Once again, that is going to be distributed to both of them. So that is 4 times 2, which is 8 hydrogens. Now, in terms of oxygens, we still have 6 here, but now we got 4 more over here. So that's going to give us a grand total of 10 in this case, which is not a problem because now we could easily go back to the other side and fix the oxygen by putting a 5 there. And that would give us 3 carbons, 8 hydrogens. And once again, 5 times 2 would be 10 in terms of our oxygen. Any questions on that one there? All right, a couple more. Let's balance this guy here. A little diboron trioxide reacts with water to form boric acid here. Okay, so boron on the left here, we got 2. We do have 1 on the right. Oxygen on the left, we got 3 there, plus 1 more makes us 4. On the right, this 3 does get distributed into anything in the parentheses there. So that would give us 3. And lastly, for hydrogen, we got 2 on the left. And once again, distributing that 3 in there would give us 3. Not much to work with here. So boron seems like the good move. So we'll put a 2 there in front. And when we do, that gives us 2 borons. Now, in terms of oxygen, this is 3 times 1, but we also then need to times it by the guy in front. So that would be 6 total. Same thing with the hydrogen here. That's going to be 3. And then we also need to times it by that guy in front, which would give us 6 hydrogen. So anything in parentheses gets distributed to the parentheses. Any number in front gets distributed again to everybody behind there. At this point, we did something. We fixed the boron there. In this case, hydrogen, probably the easiest thing since oxygen's in a bunch of places, right? So to fix the hydrogen here, we could get a 3 there in front of the water. That is going to give us 3 times 2, which is 6 hydrogen. We still have 2 borons. Now, in terms of oxygen, we have 3 here, and this guy, again, gets distributed to both. So that's another 3, which is 6. And now we are balanced at that point, yeah? Any questions on that one there? So again, you got parentheses, you got to distribute, and then front number, again, gets distributed to everybody on the back end there. Any questions on that one? All right, then let's take a look at one more here to finish it up here. Actually, let's look at 2 more. Let's take a look at both of these here. Let's do this one, FeSO4 plus Na3. Actually, we'll do Okay, let's take a look and see how we're doing. So we'll start at the top one here. We have reactants, we have products, and we have nitrogen, hydrogen, and oxygen. Left-hand side, we have 1 nitrogen. Right-hand side, we got 1. Left-hand side, we got 3 hydrogens. Right-hand side, we have 2. Left-hand side, we have 2 oxygens there, and 1 oxygen there, and 1 there, which makes 2. So clearly here, it is just the hydrogen that is not balanced. We have 3 on one side and 2 on the other. Again, common number there would be just multiply those together. We get 6. So we really want to actually put some coefficients on both sides in this case to start with. To get our hydrogen on the right to 6, we need to put a 3. To get our hydrogen on the left to 6, we do need to put a 2 there. And that would get us on the left-hand side 2 nitrogens. Again, this being distributed. That would give us 2 times 3, which is 6 hydrogens. And we still have 2 oxygens. Right-hand side, we have still 1 nitrogen. Again, 3 times 2 would be 6 hydrogens, and 3 times 1 is 3 plus 1 more over there, gives us 4 oxygens in this case. So we managed to fix the hydrogen, but screw up everything else. So next easiest thing to fix should be the nitrogen. We just need to lay up a 2 there. And when we do, that will give us 2 nitrogens. We still have 3 times 2, which is 6 hydrogens. In terms of oxygen, we have 2 there, plus again our 3 that's over there. I think that's 5 at that point, yeah. All right, so we now clearly have nitrogen and hydrogen balanced. We are not balanced on our oxygens. We clearly do not want to touch anything on the right-hand side. So really the only thing we should think about is coming over here. And in this case, we basically need to turn 5 into 2. So this is a case where a fraction might be a good idea. And when you do the fraction, we're looking for 5. And that should be the number up on top. And the bottom number should match this number, which is a 2. And if we do that, we end up with 2 nitrogens on the left. 3 times 2 is 6. And when you take 5 halves times 2, those cancel and you end up with 5. Yeah. So we are balanced in this case, again, using the fraction to do so. Can I leave the fraction? I cannot. So we do need to clear the fraction, and we're going to multiply. I think they call that the denominator still. So we're going to multiply everybody here by the denominator, which is 2. And that would give us 4 of the NH3. That will give us 5O2. That will give us 4NO plus 6H2O in this case. And now if we didn't screw up here, we should still be balanced. We have now 4 nitrogens on the left and 4 on the right. We have 4 times 3 there is 12 hydrogens on the left. 6 times 2 is 12 on the right. And 5 times 2 is 10 oxygens. And on the right-hand side, we have 4 oxygens here and 6 more here make 10. We are good in that case, yeah? So again, you can definitely use a fraction, but you do have to clear it when it's all said and done. And once again, just choosing the fraction, top number is the number you need. So like here, we needed 5. Bottom number should match the subscript. And then you'll probably always pick the right fraction no matter what you need in that case. Any questions on that particular one there? All right, so the last thing we sort of talked about as well when we were kind of previewing these equations is a situation can have developed like we have in this last sort of reaction here. And in this last reaction, we have a bunch of polyatomic ions on both sides. And we do have the same polyatomic ion on each side. So when we do have reactions that involve these polyatomic ions, and they're on multiple sides, but basically look the same. So for example, here we have a sulfate, and we have a sulfate, we have a phosphate, and we have a phosphate. Because usually they're polyatomic ions, and you might have more of them, if you do go element by element, which you could do, there's just a lot of like keeping track of multiplying in and multiplying out. So sometimes the best approach is to keep them together and just balance those polyatomic ions on each side. And that's really where you should start. So for example, in this case, if we look at the sulfate on the left and the sulfate on the right, we have one of each, so we don't have to worry about it. If we look at the phosphate on the left and the phosphate on the right, we have one phosphate on the left and two on the right. So that's a good place to start. So to fix that, we can put on the left-hand side there to balance out our phosphates. So since we have two of them here, we could put a 2 right there. That gives us 2 phosphates. That also immediately changes the amount of Ks that we have, right? And that's actually where you should go next. So since I just messed up the Ks there, I now have 6 Ks on the left, which means on the right-hand side to fix that, I should put a 3. That gives me 6 Ks on the right to match. That also means that I just messed up the sulfate, and that gives me how many sulfates? That would give me 3 total SO4s, right? Basically. So that's where you should go next. So to fix the sulfate on the left, I should put a 3 there. That gives me 3 sulfates on each side. Also gives me 3 coppers, which is what I need as well. So that everything falls into place. So it's much faster, a lot, probably less room for error. If you have multiple polyatomic ions, they do obviously have to look the same on both sides. They got to be the same ion on both sides. That is a good place to start with in terms of balancing. Just balance them as units rather than individual elements. And what usually will happen after you put a few coefficients down, everything will sort of fall into place. But just like we did here, we started with the guy here that then told us we should go to potassium next. We did potassium, told us we should go to sulfate next. We did sulfate, told us we should go to copper. So you could just kind of follow where it takes you as you're trying to balance those polyatomic ions. Any questions on that there? Again, probably a lot easier than trying to go sort of element by element, especially with those polyatomic ions that are there. It makes it a lot less in and out and in and out in terms of keeping track of everything. Question on balancing here. Yes. So again, you do need to obviously be able to balance equations, and you should always make sure that the equation you're dealing with is balanced. As we'll talk about a little later on in this chapter, if you do not have a balanced equation, it's going to screw up all the rest of your calculations. So pretty much there really kind of like no situation usually in chemistry where you would use a non-balanced equation. So it's just something just automatic, got to be balanced, make sure it's balanced. Any questions on any of that there? All right. You don't get the, okay. We can if I could think of one. Let me think of one. Let me see here. Let's do. All right, so let's take a look at this one here, for example. We'll hope for the best. I think we might be okay. I think we might have looked at it, but let's look at it one more time. So if we do our same sort of process here, reactants and products, we have carbon, hydrogen, and oxygen. So if we take track of everything, we have 2 carbons on the left, 1 on the right. We have 6 hydrogens on the left and 2 on the right. We have 2 hydrogens on the left. And once again, here we have 3 hydrogens there. So much like the other one, it kind of looked like this. We'd probably start with the carbon, which means we would just put a 2 here. And that's going to take care of the carbon, which would be 2. That would be another 2 for the hydrogen. And again, our oxygen here, that's going to be 4. And 1 more makes 5 in this case. Yeah. At this point, we fix the carbon. The next easiest thing to fix would be the hydrogen. So we would put a 3 here. And now we'll see if I did it right or not. All right, so we got 2 carbons. We have 3 times 2, which is 6 hydrogens. And now in terms of our oxygen, we have 4 there plus 3 more there. That is 7. There we go. Yeah. So at this point, the only thing that is not balanced is the oxygen. And again, this commonly comes up in a situation like what we see here, which is we have sort of the diatomic element version of it. And we also have that element in a couple of other spots on the right-hand side. So that's usually a situation where that will sort of develop where a fraction would be the best move here. And the reason why the fraction here would probably be the best move is we clearly balance everything on the right-hand side. You know, we're pretty much done. We don't want to go back and start figuring out bigger numbers and stuff like that we don't need to do. So really what we're looking at in this case is we have a 7 is what we basically need because everybody on the right-hand side is pretty much locked into place because we're not going to change any of those numbers. So we got to end up with a 7 for the oxygen. Where we're sitting now on the left-hand side is we're sitting at 2. So we basically got to turn a 2 into a 7. And that's where the fraction can be really helpful to do so. So when we are picking our fraction to use, the number on top is the number we need. The number on the bottom is the number that matches the subscript. So that means in this case, we need to end up with 7. So 7 should go up on top. The subscript here is a 2. So that is what should go here. And now we've chosen the correct fraction in this case, because when we take 2 for carbon, we still have 6 hydrogens. And when we multiply 7/2 times 2, and we're doing that because there's a 2 there, the 2's cancel and we end up with 7, which technically means at this point, this equation is balanced, but we cannot leave the fraction. So what we have to do is multiply the entire equation, not just the fraction, by the denominator. And in this case, the denominator here is 2, which in a lot of cases is going to be 2, and in most cases. And when we multiply that 2 across, we will end up with 2C2H6. Again, 7/2 times 2 is 7. That gives us 4 CO2 and 6 waters. Again, we're multiplying the 2 to everybody in the front here. And that then will give us a balanced equation that has all whole numbers, and we're still balanced. So in this case, we have 4 carbons and 4 carbons. We have 12 hydrogens over there. 6 times 2 is 12. 7 times 2 is 14 oxygens. We have 8 oxygens here and 6 more there. Should be whatever I said there, 14, I think. Yeah. So we are balanced. So you want to choose a fraction that basically will give you the number that you need. And again, basically to choose it, number you need on top, matching subscript number on the bottom, you'll be in good shape. Question on that there. And again, that is a very common situation where this occurs, like we see in this problem or the previous problem where we had, where maybe I got rid of the previous problem. Where it was up. This problem here, I went way back, I think, huh? Where did that guy go? I'm not sure where he went at this point, but wherever other equation we're doing, you'll typically see the element by itself, and again, the element in a couple of spots on the right. Other questions on that? Do you have to use a fraction every time? You do not. So again, it's just sort of a case where, you know, it happens where you have those elements in multiple things. Now, some people don't even necessarily need the fraction. They could just see the larger numbers, and that's fine. Or if you see bigger numbers, you can balance them. The only thing is, if you decide to use bigger numbers, you just got to look and make sure you can't reduce them all down back to a smaller set of number to still whole numbers. So, you know, there are situations where people won't use a fraction, but they kind of see larger numbers to balance it. But again, you do need to make sure you reduce it back down if necessary. Question on balancing here. Okay. So don't go fraction crazy and try to use it in everything. It is sort of a specific situation where it should be used. Okay, the next thing we're going to talk about then is, obviously, as I mentioned, you want to make sure that you always have the equations balanced. We're going to talk about different types of reactions, ways to classify reactions. There's really kind of two big classifications of reactions. There are what are referred to as redox reactions. And there's basically what are referred to as double displacement reactions. Pretty much all reactions will fall really underneath one of these two umbrellas. And there are multiple ways that you could classify the same reaction depending on what you're looking at, but they will ultimately all come down to be either falling under the left-hand side umbrella or the right-hand side umbrella here. And as we will see in a later slide, there's really also, it comes down to really three things as to why a reaction takes place. A reaction really takes place because you either formed a solid, which is sometimes referred to as a precipitate, you either formed water, or you had an electron that was transferred. Pretty much all reactions boil down to one of those three things pretty much happening as to really the reason why it does take place. And again, depending on sort of what you're looking at, you may classify the same reaction in a different way, but ultimately they do all fall under either sort of that umbrella or that umbrella right there. So let's first look at a certain type of reaction, which is sort of the redox reactions and sort of what is happening in a redox reaction. And we'll see more redox reactions as we go through sort of organic chemistry, but it can be related to general chemistry type reactions as well. So oxidation reduction reactions are also just generically referred to as redox reactions. And basically, oxidation has a few definitions. Oxidation in a lot of cases means that something has lost electrons. So something goes through an oxidation, it is basically losing electrons. Reduction is something that has gained electrons. So something gets oxidized, it lost electrons, something gains electrons, it has gone through reduction. Sometimes people remember these things by Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. You can put them together, put Leo the lion on the oil rig, he goes grr. You don't have to choose, you can have them both in this case. But let's talk about how can we know maybe if something is maybe being oxidized or something is being reduced. And we can know that by what happens when somebody loses electron versus what happens when somebody gains electrons. If somebody loses electrons, do they become more positive or more negative? They do become more positive because they have more protons than electrons, right? So more positives than negatives. So if somebody goes through oxidation, they typically become more positive. And if somebody goes through reduction, they typically become more negative because they have gained electrons. They have more negative charges than positive charges. So a very simple way, if you're ever not sure what is happening to something, and it is a redox reaction, you could actually follow what is referred to really as the oxidation state, but we'll kind of call it the charge, if you will. But it truly is the oxidation state. And as you look from the reactant side to the product side of the reaction, if somebody gets more positive, then they're going through oxidation. And if somebody gets more negative, they're going through reduction. So a very simple number line, like they do in math, positive to the right of 0, negative to the left. if you see that the oxidation state or the charge of something changes and becomes more positive, like moving in this direction, it is going through oxidation. If you see somebody is gaining electrons and becoming more negative, so their charge changes and kind of is becoming more negative, moving in this direction, something is going through reduction. So that's a very sort of simple way. Just follow the charge from one side to the next. So if you move kind of to the right there and become more positive, it's going through oxidation. If you move back to the left there, you become more negative and it's going through reduction. So let's take a look at sort of an example of this. And this, by the way, is what is occurring in all cases when you take a metal and a non-metal together, because as we talked about, when a metal and a non-metal come together, this guy sends over electrons to the non-metal, right? Now, how can we tell sort of what's going on in terms of the charges or the oxidation state? If you have anything that is basically by itself, not combined with any other element, it's just really that element by itself, it has an oxidation state or a charge of 0. So sodium over here by itself has a 0 sort of oxidation state. Chlorine over here has also a 0 oxidation state. It is only when those two guys come together, the metal and the non-metal, that they actually start to gain charges. So when that metal and non-metal happen on the right-hand side, my sodium is now a +1 charge and my chloride is a -1 charge, right? So they balance out to 0 as we talked about. So if we're looking at what's happening here, let's take a look first at the sodium, right? So the sodium is starting at a 0 charge on the left, right? And it is heading to the right where it's becoming +1, which means it is moving in that direction. It's becoming more positive. So the sodium is being oxidized or reduced. It is being oxidized here. It is losing electrons, like we actually know, by the way. And if we look at the chlorine here, chlorine on the left-hand side started at 0, which is like here. And on the right-hand side, it ended at -1, which is moving in this direction, right? And that is becoming more negative, which means the chlorine here is being reduced. So again, that is how you could kind of use that number line to figure out what is being oxidized and what is being reduced in this case. But by the way, in a non-metal, which one should always be oxidized? The metal, because it's always the one giving away the electrons, right? And the non-metal should always be the one that's being reduced in that situation, because it's always the one that is basically accepting the electrons. So the reason this sort of reaction takes place is it's a redox reaction. It's basically electrons being transferred, which is one of the reasons why a reaction takes place. And we get the formation here of sodium chloride. Any questions on that there? Yeah. Here's another example here. This is magnesium and oxygen making magnesium oxide. This is magnesium by itself. No oxidation state or charge. This is oxygen. Naturally, the way it comes also has 0. When these two guys hook up, the metal and the non-metal, magnesium is a +2, is group 2. Oxygen is group 6, which means it's a -2. So in this case, the one being oxidized is... it is the magnesium. Again, we can see that because the magnesium on the left is starting at 0, ending at +2, right? Going to the right, becoming more positive. The oxygen is starting at 0, and on the right-hand side, ending at -2, becoming more negative. So again, here, this is being oxidized. This one is being reduced. Question on that. Again, it follows what we just talked about, magnesium, the metal, being oxidized, and oxygen being the non-metal, being reduced in this case. Questions on that there? So you may be saying, you know, if there's always a metal and a non-metal, you know, why do you need a number line? Let's say we have this situation where maybe we had this iron going to this iron. Is the iron being oxidized or reduced in this case? Oxidized. I might have heard reduced. So let me see as well. So that's both answers. So let's take a look at it. Clearly on the left-hand side, iron has what charge? +3. Right-hand side, it has a +2 charge. So iron is starting here at +3, which is here, then moving towards +2, which is moving in that direction, which means it's actually becoming more negative and means it's actually being reduced in this case. Yeah. So again, that's why it's helpful to kind of know that thing. You won't always necessarily maybe have a metal and a non-metal together. You could use it for things that, how we see, both have positive charges as well. Question on that there. All right, so those are two very common definitions of oxidation and reduction, which is either the gaining or the losing of electrons. When we get to organic chemistry specifically as well, we will look at a couple of other sort of definitions of oxidation and reduction, which works really well for organic molecules because frankly, they are sharing electrons. There's no charges. But we'll talk about them here just to add them to our list. Another definition of oxidation, in addition to losing electrons, is that it gains oxygen as you go from reactants to products. So something gains oxygen going from reactant side to product side, it's also being oxidized. And reduction is, again, sort of the opposite here. Reduction is gaining electrons, or if it lost oxygen as you go from reactants to products. So if we look over here at this one, we see that the sulfur has some oxygen. And over here, it had 2 oxygens. And over here, it ended up with 3 oxygens. So the sulfur gained oxygen, which means this guy is going to be oxidized and this guy would be reduced. Now, one of the nice things about oxidation and reduction is this: if you could just figure out one thing, who's being oxidized, who's being reduced, by default, the other guy is doing the opposite thing. They always occur together. So if somebody's being oxidized, there's somebody else there being reduced. And if you could just figure out one of those guys, then the other one is the opposite of what's going on. So like here, I was able to figure out the SO2 was being oxidized. So by default, what that means is the oxygen there has to be the one that is being reduced. How about the bottom? Which one's being oxidized? Which one's being reduced here? By the way, those always occur on the left-hand side, oxidized and reduced. What do we think? Did the copper gain or lose oxygen as it went from left to right? A loss. So something that loses oxygen is reduction, right? So this guy is being reduced. The hydrogen by default would be oxidized. So again, the only thing that's left would be the opposite. In this particular case, we actually have a metal, which means we could actually use our number line here to help us. What is the charge on the copper here? It is +2, right? Oxygen is -2, right? Charge on copper by itself is 0. So if we do our number line here, we're starting with copper at +2 and it's ending at 0, right? So it's becoming more negative, which means it is reduced. So it tells you the same thing. So in this case, since we did have a metal there, we could actually use that to help us determine it as well. And because I was able to figure out the copper, once again, the hydrogen is the opposite just by default. Question on that there. All right. One last definition of oxidation and reduction is hydrogen. We oftentimes will look at hydrogen as well. And adding it to our definition here, oxidation is the loss of electrons, the gaining of oxygen, and the loss of hydrogen as you go from reactants to products. Reduction is the opposite here. Reduction would be our gaining of electrons, our losing of oxygen, and our gaining of H2. So when we look over here, we see copper, we see carbon, which is like copper without the U, that is carbon, that has hydrogen. On the right-hand side, hydrogen is no longer with the carbon. That means that it get oxidized or reduced. So it actually lost hydrogen, right? So when you lose hydrogen, that is something that is oxidized. So this would be oxidized. By default, this would be reduced. By the way, you can use any definition you like. What happened to carbon as it went from left to right? It actually gained oxygen, yes, which means it is also oxidized, yeah. So you can use any of those definitions. They all should tell you the same thing in terms of what is being oxidized, what is being reduced. In this case, again, the carbon is losing hydrogen as it goes left to right, which means it is going through oxidation. It is also gaining oxygen as it goes from left to right, which also means it's going through oxidation as well. So you can use any of those three definitions. We will definitely see the oxygen and hydrogen definition a lot more when we get to organic chemistry. But in regular reactions, we oftentimes will just look at the gaining or losing of electrons in a lot of cases. Any questions on oxidation, reduction, any of those there? Yeah. All right, so as I mentioned earlier, there really is sort of three reasons why a reaction does take place, which is, again, a solid being formed, water being formed, or some type of transfer of electrons. And as I mentioned at the beginning, there's really two big umbrellas. These two basically fall under the double displacement type reactions that we'll talk about again. And this guy is all about basically the redox reaction. So that is basically where those two basically come into play. All right, so let's take a look at some of these here. The first type of reaction is a synthesis or combination reaction, and this falls under the redox umbrella here. So although it is a redox reaction that's occurring, synthesis or combination reactions is what it sounds like. You basically take a couple of things and make one thing. So multiple things make one thing. You're basically putting it together. As we see here, this is hydrogen and oxygen. Two things make one thing. Two things make one thing. Once again, in this case of the water being formed, although it is a synthesis and combination reaction, it is still a redox reaction because this guy has no charge. This guy has no charge. This is +1 for hydrogen and -1. -2 there for oxygen. And that means that if we do our little kind of number line there correctly, we look at the hydrogen started at 0, ended at +1, which means it's becoming more positive, which means the hydrogen here is going through oxidation. If we look at the oxygen, it started at 0 and ending at -2, which is moving in this direction, which means it's becoming more negative. So it is becoming reduced in this case. So although these are both classified as a synthesis or combination reaction, they do fall under the big umbrella of still a redox reaction of what is going on. And obviously we saw that with this reaction we talked about earlier. That is also a redox reaction, but it can also be classified more specifically as a synthesis or combination reaction that's taking place. In addition, the other one that we saw, which was this one, I think. This is also could be classified as a synthesis or combination reaction, right? Two things make one thing. It's also a redox reaction as well. Bless you. Again, as we saw, this one from 0 to +2, this one from 0 to -2. So again, you can multiply classify the same reaction in a couple different ways. Any questions on that there? The opposite of that is a decomposition reaction, and in a decomposition reaction it is basically the opposite of putting it together. This is also a redox reaction. So this reaction also falls under the big redox umbrella. Here we have an electrical current run through water. So one thing makes multiple things. And again, that is still a redox reaction. And mercury here, a little mercury 2 oxide going to our mercury liquid plus some oxygen here. This is also one thing making multiple things. If we look at what's happening with the charges on these guys here, the mercury here is +2. Mercury on this side is 0. Oxygen here is -2. Oxygen here is 0. So when we look at our number line here and we look at the mercury, mercury started at +2, ended at 0, which means it is getting more negative and is going through oxidation or reduction in that case. It is reduction. Yeah, so it's going through reduction. By the way, once I figure that out, I know the oxygen here is going through oxidation. And I can figure that out as well by oxygen starting at -2, which is here, ending at 0, which is moving in that direction, more positive. So it's going through oxidation. So synthesis and combination puts it together. Decomposition basically breaks it apart. They are both under the true reaction of redox reactions taking place. Any questions on that there? Another reaction that does fall underneath the redox umbrella is a single replacement. So this is also a redox reaction. And in a single replacement, you have basically an ionic compound. So that's how you know. And you have something that is uncombined by itself, like a metal. And normally a metal here by itself will have no charge, as we've been talking about. And what will happen here is the metal will come in and kick out the positive guy. And when it kicks out the positive guy, that is when it'll get a charge. And it will make a new ionic compound. And that guy, I was going to have to stop, drop, and roll. I wasn't sure. All right, so that guy that comes out there, it works for all emergencies, stop, drop, and roll. You know, it's all right. The guy that comes out that was positively charged before will end up with no charge as well when it does that. Now, you could also do this with a non-metal as well. So you can have that first guy being a non-metal plus an ionic compound. The difference is here, the non-metal doesn't have a charge to begin with, but when non-metals get charges, they actually become negative. So it'll kick out the negative guy in this case. And you will result in a new ionic compound here. And our guy here will come out by itself. In order for this reaction to actually take place, whatever is coming in needs to be more reactive than what is replacing. So whatever is coming in needs to be more reactive. So that sort of element coming in, it needs to be more reactive than what it is replacing. So if it is not more reactive, then that reaction will not take place. So you won't get a reaction. So this one here, where we look at zinc, this is how I know it is sort of a single replacement. I got an element by itself. I have this, which is an ionic compound. So I know that this zinc is going to be positive when it does get a charge. So it's going to come in. When it does, it kicks out hydrogen by itself in its elemental form, which are bubbles and gases formed. And it will have no charge. At that point, the zinc will then get its normal +2 charge. And the chloride here would be -1 in this case. So that is a single replacement reaction. Again, if you tried to do this with copper instead of zinc, it will not take place because copper is actually less reactive than hydrogen. So not all of them will always work. It does have to be more reactive. So a single replacement reaction always has that set up. You got one ionic compound, one element by itself, and that is sort of how you could recognize it again as a single replacement reaction. Once again, it is also a redox reaction that's taking place. If we look at the zinc started at 0 and ended at +2, heading to the right-hand side there. That means the zinc is oxidized or reduced in this case. It is oxidized as it's becoming more positive. That means in this case, what is being reduced? It is the hydrogen here. The hydrogen on the left-hand side is starting at +1. And on the right-hand side, it's ending at 0, which means it's going in that direction. So it is actually the hydrogen here that is being reduced. What is happening with the Cl? Does it change just from left to right? It doesn't. It has the same charge. So there's nothing happening. It's what's referred to as a spectator ion. It's just kind of hanging out for the charge. It's not really doing much. So not everything is changing as you go from left to right. There should at least be a couple of things that are changing, being oxidized and being reduced at the same time. So although this is classified as a single replacement reaction, it does fall still under the big umbrella there of redox reactions. Any questions on that there? Now, a precipitation reaction is a classification of really a double displacement reaction. And this is the other sort of umbrella. And then a double displacement reaction, how you recognize that is, frankly, you start with 2 ionic compounds. So that is how you know that you have a double displacement reaction taking place. In this case, the 2 positive guys will switch partners. So those 2 positive guys will basically switch partners and make 2 new ionic compounds. So we'll have A and D and C and B in this case. Now, double displacement, which is that basically the 2 positive guys switch partners, is the big classification. And if one of these guys makes a solid, that is what is more specifically referred to as a precipitation reaction. So a precipitation reaction is a more specific classification of a double displacement reaction. A precipitation means that you made a solid, and if you remember, that is why one of the reasons why a reaction takes place is the formation of a solid. So because we made a solid here, that's really what is happening. Can I recognize this as a double displacement? I can. That is a positive negative guy. That is a positive negative guy. And in this case, the potassium ends up with the nitrate, like we see here. And on the other side there, the barium, which is positive, ends up with the chromate, which is negative, and that is what we get over there. So we have this sort of double exchange that occurs. The 2 positive guys switch partners. When you put them together on the right-hand side, you want to put them together like we did with naming. Make sure everybody equals 0 with the basic units of each of those ions. Any questions on that there? So looking at this guy again, we see that those 2 guys switch places. And again, our double displacement reaction taking place. Once again, positive potassium over here ends up over here, along with our negative nitrate. So they come together. And our other positive guy, again, switches partners. Our positive barium hooks up with our chromate and makes this guy here. So we get that again, double exchange that occurs. That is how you could recognize it, different than a single replacement reaction where you have just 1 ionic compound. If you have 2 ionic compounds to start with, it's going to be a double displacement reaction. And in this case, one of them does make a solid, which makes it a precipitation reaction, a more specific classification. Any questions on that there? This is another type of reaction which also falls under the double displacement reaction. This is what is referred to as an acid-base reaction or an acid-base neutralization reaction. This is also a double displacement reaction. When you have an acid, which is this guy, hydrochloric acid, and a base, you basically make 2 things. You always make water, and you make what is referred to as a salt. A salt is just an ionic compound, and water is made always from this combination. It is always the hydrogen there from the acid and the OH there from the base. And that is what will make our water on this side. And the other two guys will come together to make our salt. So the potassium there and the chloride will come together to make our potassium chloride in this case. So this is also a double displacement reaction because this HCl is a positive negative guy, positive negative. So once again, our hydrogen exchange partners here. And that is what we get. What we formed here is actually water, which again is one of the reasons why a reaction takes place, the formation of water, which is pretty much what you get when you make a strong acid and strong base together. That's why they're sometimes called neutralization reactions, because pretty much you make water is basically what you make as a result of that reaction. Any questions on that there? All right. All right, last type of reaction, finish up this little talk here, is a combustion reaction. And in most cases, a combustion reaction, most people think about it in terms of the organic combustion reaction. And in an organic combustion reaction, you have an organic compound like this. An organic compound is typically carbon, hydrogen, and oxygen is involved, or at least carbon and hydrogen. But you could definitely recognize it because on the left-hand side of the arrow, there will be O2, and on the right-hand side of the arrow, CO2 and water. If you see those three things in a reaction, it is definitely a combustion reaction. That's basically, again, when you light your Bunsen burner, that is what goes off, what's happening there. A more generic definition of combustion reaction is simply this. All you need is oxygen on the left-hand side of the arrow. So if you have any reaction that has oxygen on the left-hand side of the arrow, it is a combustion reaction. And that is why when we look at this reaction that we saw earlier, this reaction that we saw earlier right here with magnesium, that is a redox reaction, as we saw. That is also a synthesis or combination reaction, and that also could be classified as a combustion reaction, yeah, depending on what you want to look at. So that one reaction could actually be classified in 3 different ways, depending on what you're looking at. So combustion reactions also typically are under the redox umbrella of reactions. So just to summarize those things really quick here to finish, under the redox sort of umbrella where we're talking about electrons being transferred, more specific classifications are synthesis reactions, are combination reactions, they are decomposition reactions, they are single replacement reactions, and they are combustion reactions. So all those more specific ways of classifying reactions fall under the redox umbrella. Double displacement. Those are your precipitation reactions, where you make a solid, and your acid-base reactions basically fall underneath that umbrella. And all those reactions account for the 3 reasons why a reaction takes place. Everybody on the left, that's all about electrons being transferred. This is about a solid being formed, and this is about water being formed. So 1, 2, and 3 reasons why a reaction takes place can be explained by any of those sort of classifications. Any questions on that there? All right, we're going to stop there for now.